So today we are going to talk about merge sort. The code for merge sort, I'm going to warn you right now, is really, really intense. It involves two separate recursive methods. It involves a total of 3 separate methods in order to make it work. Again, fortunately for you, if the AP exam asks a question on merge sort, they're going to give you all of the code, or the question is going to be more generic. So the options of you tracing this are slim to none. You're not going to be able to trace the code. It's going to take you forever to trace the code if you're going to do that. You have to know how the algorithm works in order to understand merge sort. In addition, I was only able to find one actual question on merge sort for the AP exam. So the fact that this is really on our last lesson kind of lets you know that I don't think it's going to be on the test, honestly. But I'm going to cover it anyway, because you never know those AP people. Sometimes they decide to put something on the test that hasn't been on the test before. This is technically testable content. They do list it in the course description, so we're definitely going over it. The code is a lot more complicated than the actual algorithm. The algorithm is really pretty simple. And it involves just doing the same thing over and over and over again. And it's called a merge. So essentially the goal, of course, is to put the list in order. And the way this is accomplished is we sort the array out into smaller lists. In fact, we're going to sort them out into lists that are the size of one element to start. Break it all up to one element. Then we're going to put the lists back together in order. So first we start with pairs. Then we take the pairs and we sort the pairs into 4s. Then we take the 4s and sort the 4s into 8s. So we're always starting with a left-hand side and a right-hand side that's already sorted. And all we're doing is merging the lists into sorted order. So we look over here and say, which one's bigger at the front of the list? Put the smaller one next. Which one's bigger at the front of the list? Put the smaller one next. And you're just looking at both sides, just looking at the front of the list every time, which gives you the reason why it's recursive. Because we're doing exactly the same thing every time. So I have a really good video on this that I wanted to show you. But this is the algorithm in short. It creates a temporary array. It calls what's called a merge sort helper. So the clue that this is merge sort on the AP exam is they have lots of methods to make the sort happen. Every other sort's done with one method. This sort is done with 3. One of them being a helper for another one. And when we look at the code, you'll see exactly what I mean for that. So I want to go through, and I want you to watch this video that's here called merge sort. This is a very good demonstration of how the merge sort actually works. So pause this video and watch this one. So that's the end of merge sort. Let's take a look at some of the code, and then we'll look at comparing some of the other sorts together with merge sort. So essentially the algorithm works like this. You have this merge algorithm, and then you also have this helper algorithm. And then you have another method that ends up calling them both. So you have merge sort that uses the method merge and uses the method merge sort helper. These two methods are recursive. They do the same thing over and over again. You're going to have 2 different base cases. If you think about the way that merge sort worked, there were really 2 base cases in that. The first one involves splitting the list in half. And you continue splitting the list until you're down to single elements. So that's the first recursion that has to happen. Once the list is split into single elements, then you start merging them. The merge is the same process every time. So there's the other recursive element. So once the list is totally sorted and we stop calling merge, then that recursion's done. Once the list is split all the way out into individual elements, that recursion's done. Those two recursive algorithms, or recursive methods, work together to give you merge sort. So if we dive in and look at what this code looks like, you can see that clearly there's a lot of code here. We have a method here that is called merge sort. And you notice it's really short. The first thing it does is just sets up the arrays and sends the original array and a temporary array to merge sort helper. And that's all it does. It essentially just kicks stuff off. Then merge sort helper, which is right here, is the part that's doing all the splitting. So if from is less than 2, and from and 2 are the lengths of the array. So if from is less than 2, in other words, once we get down to that individual split of single elements, then we're done this and we start calling merge. So once this condition is met, now we're going to start merging the left and right sides using the merge sort helper and calling itself again. In addition, we merge the two lists. This is the actual merge. This is the little while loop here that's comparing the elements and choosing which element do you want, from which side of the list goes into the new list. Notice that we have to have not just one temporary, but a temporary array every time we merge lists. So when we take single elements and merge those, we need a temporary array for each one of those. We need a temporary array that holds the larger ones. We need a temporary array that holds the ones that are larger than that. So all of a sudden, this becomes extremely expensive in terms of memory. But it's really fast. Let's take a look and see how fast. So this is a visual sorting algorithm. It'll run through and kind of go through and show us how the sort actually works. You can go through and leave it on slow mode to kind of see the steps. This is a good practice to review how all the different sorts work. Selection sort, insertion sort, and merge sort are the three that are on the AP exam. Not quick sort, not bubble sort. But if you want to look at them, you're more than welcome to look at them. So let's look at selection sort. I'm going to put it in fast mode. It's sorting 16 elements. And you can see how it progresses. But even this is too slow for us to really compare them. So down here, there's a timed sort that actually runs full computer speed. It's not doing any animation. So I'm going to stop this. We're going to do a selection sort first. It's going to sort 10 arrays with 1,000 items per array. That's a lot, right? So we're going to run the sort, see how long it takes. So it took it 25 seconds to sort 10 different arrays. So in other words, it did the sort 10 times. Each one of those arrays has 1,000 elements that needed to be sorted. That's a lot of data to be sorted. 10 different arrays, 1,000 elements. It took 25 seconds. That's pretty fast. That's a whole lot faster than you guys could do it, right? It's a whole lot faster than I could do it. But let's switch it to insertion sort and see how that runs the same sort. So we're at 24 and a half seconds, right? Same sort. Wow, already done. 8.5 seconds. That's a significant difference. So with the larger size, insertion sort and selection sort do become a little different. It's still n squared for big O notation in terms of comparing speed. But when you actually check the times, for a much larger list, insertion sort is much faster. So let's do the last one, merge sort. So remember, our best time now is 8.5 seconds. Ready? Go. Did you catch it? 0.05 seconds. So if we look at the comparison for all three, 10 arrays, 1,000 elements, first we see that selection sort had, what, we're almost at, let's see, there's 3 zeros, there's 3 zeros, almost 500 million comparisons. Then we're down to half that for insertion sort. We are under 150,000 comparisons for merge sort. The time difference is staggering. So you can understand why selection sort and insertion sort really are not used in the real world, because the real world has a lot of data in it. You won't be, as a professional coder, using selection sort or insertion sort. Why do we teach it then? Well, real simple. To teach you about algorithms. That's it. Understanding the difference between an algorithm and the code. If you know the algorithm, you don't need to trace the code. And there's plenty of algorithms out there doing all different kinds of things. When we first looked at this in Unit 3, we looked at that video talking about algorithms, and they had some really cool algorithm names, like the knife, right? And one was called the something shuffler. And they all do different things. And some of the algorithms track stock markets, and some of the algorithms track prices. Some of the algorithms track prices in Amazon. Some of the algorithms predict what movies you're going to see. Algorithms are a fundamentally important concept for anyone who's going to be a programmer, especially in today's world, because today's world is all about data. This is where you're going to find your niche as a programmer in a company. So whether you decide to go into a computer company and you're going to go hardcore code, or you're going to be working inside of some other company of your field, you may decide that you don't want to be a coder. However, if you understand algorithms, you could take that and put it into any marketing field whatsoever. Let's say you want to go into politics. Understanding how the data works could mean the difference between you winning the election. Now that they're going back and looking at this election and trying to figure out how they could have been so wrong on the night of election night, saying that, oh, it's going to be easy, right? Everybody was saying it's going to be a landslide. At least all of the major medias were saying it's going to be a landslide. Hillary Clinton's going to win. And then all of a sudden, like, wait a minute. This is not going the way we thought it was. Something odd is going on. What's the odd part of that? There are now people who are paid a lot of money. And they'll be paid a lot of money over the next 4 to 8 years to figure out why the Democrats lost. It all comes down to the data and trying to figure that out and coming up with a strategy to then go forward and try to go ahead and say, hey, next election, what are we going to do different to change our results? And that's all about studying algorithms and studying data. And there's vast numbers here, huge amounts of information, so you're going to need a computer to do it. You can't sit there and do this by hand. That would be ridiculous, especially if you consider that the computer took 25 seconds to do it. Could you imagine? In their slowest sort, the computer took 25 seconds. This would take you days. At best, it would take you days. It might take you weeks to sort this. Even without using an algorithm, just using the speed of your head going, yep, and move the stuff around. Because your brain works a lot faster than an algorithm. Okay. So here's the code. Like I said, this would be a pain in the neck to try to trace. But if you understand the algorithm, it's really not that bad. It's a fairly easy algorithm. Split the list into single elements. Then start merging the list together. So, what I'd like you to do is pause the video and give this a try. Split the list into single elements. Hey, look, I kind of sort of already did that to you. That's already done. So really, all you have to do is start merging. So just start merging, and the best way to kind of organize this is like a tree structure. So these two merge, and they come down to a list. These two merge, these two merge, these two merge. Then merge all the 2s, then merge all the 2 4s, then merge the 8s, and go forward from there. So I'm going to pause the video, and I want you to try to do this. Sorry. Okay, so let's start merging this. Assume we've already split this up using our helper function all up into individual single element lists. So that's nice. On the AP exam, you don't even need to do that part. It's fairly easy to do that visually. Just say, okay, yeah, they're all singles. Done. Split it all up, single list. Now we're going to merge it all back together. That's the part we actually have to do some work. So we compare the 34 and 56, and we order it 34, 56. So we're taking these two first. Then we take the 55 and 12 and merge it 12 and 55. Whoops. Be good if I could actually, right? Here we go. 12, 55, 88 and 37, 21, 45. Okay, those two are merged. Now we're going to merge these two and these two. So 12 and 34, the 12 comes first, then the 34. So the 12 is out. Whoops. I should have done this all the way in steps. So it's 12 comes first. 12 is out. Then 34 and 55, the 34 comes out. 55 and 56, the 55 comes out. And then finally we're down to 56 because there's nothing else left. So now we'll do this. 37 and 21, the 21 comes out. 37 and 45, the 37 comes out. 45 and 88, the 45 comes out. And then finally we have 88. So now we're going to merge these two lists. So we have this list. Actually, just one big thing. Right? One full merge. So 12 and 21, the 12 comes out. 34 and 21, the 21 comes out. 34 and 37, the 34 comes out. 55 and 37, the 37 comes out. 55 and 45, the 45 comes out. 55 and 88, the 55 comes out. 56 and 88, the 56 comes out. And then finally we put down the 88, and there we go. We have our sorted list. So finally, big O notation. This is n log n. You can clearly see why this is so fast. It's a very, very fast algorithm. Selection sort and insertion sort are n squared. They're significantly slower for large lists. However, the trade-off is the amount of memory that's used. You need a lot of memory to use that. If memory for you is expensive, right, then you don't want to necessarily use this. Because you have to create a whole bunch of recursive calls. You're creating a whole bunch of temporary algorithms. So yeah, if you have all the room in the world, using this is the fastest method possible. If you're limited on space, like let's say I'm doing this on a Raspberry Pi, right? It's a teeny tiny little computer, very limited processing power, very limited space. I may say, hey, you know what? 0.05 of a second versus 30 seconds to sort that number of items. I'm not that concerned about the time at that point. I'm more concerned the fact that it can't sort it. It won't be able to sort it because it doesn't have the processing power to sort that. Now that we are in the world of Internet of Things, you know, controlling light switches, having your refrigerator do your shopping for you, we're talking about very small, low-powered computers that are in everything we own at this point. And you're going to hear more and more about this Internet of Things as it really starts to gear up and developers really kind of take these little tiny computers and build these really cool things. And it's not going to cost a lot of money. This stuff is going to be very low cost because these computers are low cost. So as a programmer, you're going to have to start making these decisions. Is it better to be fast and a lot of memory, or is it better to be slower and use less memory? So that's a programmer decision. That's really what the lesson here is, that no matter how fast you think something is, there's always a trade-off. And understanding what that trade-off is going to be important for you. So understanding how every algorithm works and what the trade-offs for those is really the ultimate lesson of this last merge sort. Here's an example of a question that they might possibly ask for the AP exam. It's a very cheap question to ask because it doesn't require a lot of paper. And it just says, which sort contains a recursive call? Answer is merge sort. That's it. That's like the easiest question they could ask. I could see that showing up on the AP exam very easily. It just tests, do you know the algorithm? So that's it, folks. Never stop coding. Good luck on the AP exam.